where we left off with the truth tables for and, or, and conditional, or rather implication statements. And I'm going to give you, as we review those truth tables, I'm going to give you these three new definitions. Okay, so we had the truth table for, let's just say, given A and B and A and B. Remember, this symbol is A and B. Is that, let me know if you can't see that. I believe that's the upper bound here for the, you can't, okay.
No.
Let me make a mark here then. I'm assuming it's somewhere there. You see, you probably can't see, but I've got horizontal bounds on the webcam. But sometimes it tells me the bounds are here, and then I get into the meeting and it like shrinks them depending on your device, right? And if you have the chat or anything on the side of Teams open, that shrinks your view too. So you can, if you'll close those, you'll have a broader view. Okay, so anyways, so we had, let's set it up like this. We have, if we were given A and B, and we wanted to consider the truth values of A and B, so possible truth values for A and B, and then with these inputs, what are the possible combinations or possible truth values outputted by A and B? So I'm just going to go through this quick because we kind of went through each of these in detail. Okay. So we had an and statement only being true if both inputs, both pieces that build the statement are true. We call this statement a conjunction. So there's a new word, is called, A and B is called a conjunction. Just a new word to describe an and statement. Because if I say and statement, that's kind of informal, so we like to have a fancy new word to describe it. That's all that is. Literally, if you look in the book for the formal definition of conjunction, it says if A and B are statements, then A and B is a compound statement called a conjunction. There's nothing else to say there. Just a word to describe this. All right. Now I'm going to move to the or. So to make things easier for me, I'm just going to erase this column. You'll have to redraw a chart, of course, in your notes, or you can just be referencing the notes, the charts that we did last class. Oops, sorry, I meant to change this to or. Okay, so we recall that this is read as A or B, and if you check your notes from Monday, you'll remember that these are true as long as one of the inputs is true, right? But false in the last case where both of the inputs are false. Okay, and what's the fancy new definition, vocabulary word for this statement? A or B is called a disjunction. A disjunction. Okay. All right. Ooh. 1 second. I just remembered my laptop's not plugged in. I'm going to run to my office, which is right across the hall, and plug it in because, as I said, my laptop is a dinosaur and it's also a diva. And if it doesn't have charge for more than like 15 minutes, it dies. So 1 second. Actually, how about this? How about I'm going to go ahead and give you the next one, and while I'm gone, you can be writing the next definition. So the last one was A implies B, or if A, then B. This one warranted a fair bit of discussion, but we finally came to, we're on the same page, that it's only false when the first part of the statement is true and the second part is false. So when it has an input in this order of true, false, then it outputs false. In every other case, it's true, And we call this, it already has several names, right? If then, an implication statement, and the new one is called a conditional, which I argue that name really fits. Wait, can we see this? Yeah, barely. Okay. This name fits because this if A then B, the output here is very much conditional. It depends on what's going on with A, right? Very much. In fact, if A is false, we can just go ahead and say that the entire statement is true without even regarding B down here. B doesn't matter here. It's the fact that the first part of the statement is false means that the entire statement, the output, is true. And we call these two rows vacuously true. All right, I'll be right back. All right, let's plug this. Excuse me. Oh, guarantee I'm going to trip over that. Oh no, it moved. Okay, let's get back. There we are. All right, new definitions, same truth tables. Let's do some practice building larger truth tables, or rather, let's do some practice looking at the outputs of larger compound statements. So how can we, so the question, the setup here is how can we consider the truth value outputs of a large compound statement? Question. Okay, this marker's done. How can we consider the truth value outputs of a large compound statement? So we've already considered the truth value outputs for like A and B, A or B, and if A then B. But what do we do if we want to consider like, A and not B implies B, something like that where there's a lot going on? Well, the answer is truth tables. The answer is truth tables. So we'll build truth tables. I'll say we can build a truth table we can build a truth table to discover the possible outputs of this statement and any other crazy statement I can come up with, right? And this isn't even that crazy. I've still only got 2 letters, right? Like, what if I put 3 letters? Okay, so that's what we're going to be doing today. I'm going to be building weird statements like this. We're going to be constructing truth tables out of them, and I'm going to walk you through how to do that. And then will be the objective will be the last column of the truth table will be this entire thing, and we'll list its possible truth outputs underneath that column. That's going to be the ultimate goal. of each of these truth tables that we do for each of these compound statements is that the last column is going to be the whole thing. And we're going to explicitly list its truth possibilities underneath it. So let's actually work with this one. Let's actually work with this one. Okay, just giving you a second to write it down. Do I remember what it was? Yes, okay. Oops, no, that's fine. A and not B implies. That was it, right? Was it and? I hope so. You guys will tell me if it's wrong, right?
Yes,
All
right.
Cool, thank you. So what do we do? What do we do here? We set up a truth table. Now, when there's a lot of stuff going on like this, you're going to want a fairly wide truth table. So in your notes, just a heads up, you're going to want a fair bit of horizontal space. We're still going to have the first two columns being A and B, and we're still going to have only those four combinations because there's only two letters to begin with. So you're going to start off with those four combos that we always start off with when there are two variables, or two, well, they represent statements, right? Two simple statements. But I am going to extend this all the way out there because I'm going to have several columns, and I'll explain how I know what those columns are going to be. But first, let's get these combinations down. Let's see. Okay, so you can, okay, it's the lower bound. All right, the first thing I need to consider is I need to consider anything that's negated. Any variable, or rather any simple statement, any letter that's negated up here needs its own column. Okay, so that means the negation of B needs its own column. It's the negation of B needs its own column, but don't be worried about it because literally all you do to negate a variable or to negate a simple statement is you flip its truth values, right? That's what like a logical opposite is. A negation just means like if it's true, it should be false. So you literally just flip the B column here, true, false, you just flip it. So it's going to be false, true, false, true. Now again, why did I include the negation of B? Well, because it's built into my statement up here. That's why it's here. Now my next step is going to be figuring out what the truth output of this thing is. This thing here, A and not B. A and not B. I'm not going to do A and B because A and B is not involved up here. It's A and not B. So I'm going to say my next column is A and not B. Now, this is where, remember I wrote those little facts at the end of last lecture about each different symbol, the and, ors, and if-then statements. Whoa. And I said that I gave you some clean-cut facts there, right? Those facts are going to be useful here, okay? So what is the fact about ands? They're only true if both inputs are true. And by the way, what are the inputs I'm talking about now? What two columns am I looking at to decode this? I'm looking at this column, A, and this column, not B, right? Those are the two inputs for this conjunction, these two. All right, now it's only going to yield true. It's only going to yield true if both pieces are true. So if I'm considering these two, the first one is going to be false. The first one is false. So true, false, that gives me a false there. The next one, I see two trues. So that is the only way a conjunction, no, did I say disjunct? It's a conjunction. The only way a conjunction can yield true is if both inputs are true. So that one's true. And the other two are false. Okay, Any questions about that one? Big thing to note is you need to make sure you're looking at the right columns. Two things, really. The right columns, so make sure you're looking at these two because those are the pieces that build it. And also know your facts about the and symbol, the conjunction. Know that it's only true. That's something, each time you're looking at these, say, okay, it's only true if both pieces are true, so that's false. It's only true if both pieces are true, so that's true. And just repeat that rule for each little row here, for each pair of inputs to find these. Okay, so now I've got this thing, this whole thing here condensed into 4 possible truth outputs. That's this part here, the first part of the conditional. So now I'm ready to write the entire statement here. A and not B implies B. So why do I say that we're ready to go ahead and write the full statement? Once you have the two pieces of the greater compound statement here, which the greater compound statement is this whole thing implies this little thing. Once you have those two things as isolated columns, which I do, I have this thing, right, as an isolated column. And of course I started with B, right? B was all the way back here. Once you have them as their own separate columns, now you're ready to consider the entire thing, the entire compound, the greater compound statement. So what am I looking at? I need to be very careful about the order here, okay? The order here. It goes, if this, right, this is first, then this, right? So my first combo here is if false, then true. And you can go look at your implication table, which would be a nice reference, right? To see what happens in the false true column, or you can just remember they're only false if you have the combo true, comma, false, right? True, false yields false for these, and the rest of them are true. So that means here, when I have the opposite direction, false, true, that leaves me with a true. So you see the direction is very important. My columns are out of order because of the way I had to build the table. So it's very important that you're thinking, if this, then this. Now here, if true, then false, that's the only combination that yields a false. Right? So is that the only one I have? Yes, the rest of them have the first part being false, so they're going to be vacuously true. So it's actually going to look very similar to the just straight up A implies B table, which is just a coincidence here. Okay. All right, so any questions about that? Or maybe you just want to see more examples. Okay.
Yes, could I see another example?
Yeah, we're gonna do several. So let's see, I'm gonna make up a new one. I just realized doing 3 variables on here is gonna be, with this space, is gonna be quite a nightmare. All right. We won't do 3 letters yet. Let's stick with a 2-letter compound statement. How about negation of A and B? That's kind of a, you know, we went kind of hard with the first example. Let's look at a, maybe a less intense one so you can let some of the ideas about building the truth table settle in. By the way, I'm not writing what example this is. This would be example 2. If you like to keep your notes organized, enumerated by example, and I'm not going by the text today, I'm just, normally at home I have the text open next to me and I just go through it, but all right. So we have the negation of this entire statement, A and B. So always starting off with separately, A, B, and there are 4 combinations: true, 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 false, false, true, false, false. All right, so what are we gonna need? Any ideas about what the first column should be here? Like what we should put in the first column? How about,
Not A.
what's that?
Not A.
Is
Or
not
negated
A
A.
explicitly included though? It's
No.
not. Yeah, not
You need to do
explicit.
A and B first, so you can do
Yeah,
the opposite
we
of it.
want to, you're on the right track with thinking that we want to include the negation, but the thing is, it's not explicit, it's not like this, right? If it was, then yes, we would want to include the negation of A, but in fact, these are very different statements. So the first thing we'll want is that internal piece here. And how do you know? Well, it's kind of going to boil down to like an order of operations, kind of like an analogous thing. Obviously, we're not dealing with like addition and subtraction and exponents, but there's kind of an analogous thing going on here with order of operations where we know that since this is grouped in such a way with these parentheses, that this operation comes first and then the negation. And that should be reflected in our table. This should come first. And then the last column will just straight up be the negation of it. So which is the entire statement. So we got our table set up. So now we're recalling our rules for conjunctions. They're only true if both inputs are true. So this is just a straight up, this is like the classic table, conjunction table I gave you where it's true, false, false, false. All right. How do I construct this column? Well, this column is just the negation of this column, right? Because that's its input, here's its input, and I'm just going to negate it. So I'm literally going to flip this entire column to
False,
false.
true, true, true.
Yep, that's it. That's it. Okay. Cool. Let's do a similar one. I just had a great idea. Example 3 will be the negation of A or the negation of B. Okay, so first 2 columns. Oh yeah, you're gonna, in case you haven't figured it out, you're gonna be burning through a lot of paper for these 2 sections. For this section, which is 3.2 and 3.3, just because of all the tables that we're gonna make. Okay, so this time the negations are explicitly attached directly to a actual variable. So we're actually going to need 2 extra columns here for the negation of each. Oh, let me write my original truth values before I start getting too ahead of myself. Okay, so I'm going to have the negation of A here and the negation of B here. I'm literally going to take the A column and I'm going to flip its truth values. So I'm looking at A for the negation of A. I'm going to have false, false, true, true. For the negation of B, I'm just going to take the B column and flip its truth values. By the way, if you take, I don't know, probably none of you guys are computer science majors, but if you end up going in any field that requires you to have any kind of like computer programming knowledge or anything like how a computer thinks, like computer logic, these tables become super helpful. You replace these T's and F's with zeros and ones, and then anyways, then it can be applied to, I'll just call it computer logic. Okay, so we've got our two negation columns here, which are the pieces that build this greater disjunction statement. So I'm going to go ahead and say we're ready for that now. So we've got the negation of A, so this column or this column. Okay, now it's only false if both pieces are false for a disjunction. So we have the first one being false. The rest of them are going to be true, right? Because a disjunction is only false when both inputs are false. And of course, I'm looking at the first column, or the third and fourth columns here. There we go. Okay, so 1 second. Okay. Sorry, I was thinking on the side over there. All right. Any questions about this one in particular? Or anything to note about it? Any comments or anything? All right. I actually want to make it. Oh, go ahead.
How did you do the last one?
The last one is coming from combining these two. These two columns, right? These are the two pieces that are building the disjunction statement, the negation of A or the negation of B. And then just using the rule for ORs, which we covered last time. An OR, a disjunction, is only false if both inputs are false. And this is the only row where both inputs are false. Hence, the rest of them are true.
Thank you.
Yep. Now, I want to make a note before I move on to example 4. Before we just keep going through all these, examples of truth tables, I want to make a note about this compound statement's truth values compared to the last one we did. Which was the same. Okay, so you can just write down, you can say, note that example 2's truth value outputs were the same as example 3's. I'm just calling to mind, just reminding you, this is what happened. Okay, so what do we say here? Shoot, I need room. I'm gonna leave the statements up here, but erase their little columns. Two compound statements. Are said to be something. We've already looked at several different ways to just describe two things being the same, right? Remember sets, we talked about two sets being equal versus being equivalent, right? So in math, we like to say there's hundreds of different ways to describe two things being the same, right? Because how are they the same, right? Now here, these two statements are the same in the sense that they have the same truth value outputs. Two compound statements are said to be, and here comes the fancy word for same, logically equivalent. Logically equivalent. if their truth, let's just say truth output. I've been saying truth outputs, which is maybe a little informal. I'm trying to make sure, I'm thinking ahead, making sure that's not going to be a problem to say that here. I don't like to be technical unless we have to be technical. Yeah, I'm going to say truth outputs. Meaning, when I say their output, I mean like that final column, right? That last column in the truth table are the same. Looks like this green marker's done too. Ooh, fresh. All right, I'll throw this one away. Okay, I'll read it to you in case you can't read it that well because it's big marker's kind of petering out. Two compound statements are said to be logically equivalent. That's the definition, logically equivalent, if their truth outputs are the same. We denote it by, oh, that's so much better. Denoted by the symbol, it's like an equal sign, but with 3 bars. Denoted by that. All right, so I'm going to erase this. I'm going to rewrite these with my brand new fresh marker and with the symbol in between, and we'll talk a little bit more about them. Let's say okay, there's the negation of the negation of A and B is logically equivalent. So the way I read this is the negation of A and B is logically equivalent to the negation of A or the negation of B. Now, if you recall, we had some laws in the set theory chapter, the end of 2.4, that sort of described the complement of a set distributing over an operation of union or intersection and flipping that operation. De Morgan's laws, right? De Morgan's laws for sets. This is De Morgan's laws for logical statements. It's kind of the same thing. Think about the distribution of the negative sign, right? The negation, and also flipping the operation. It's very much analogous to what we had before with like A union B complement being equal to A complement intersect B complement. And then there's two of each of these, right? There's the one where you slap an intersection here and then put a union here. Similarly, there's another De Morgan's law for compound statements that looks like this. You can say, what if I have the negation on the outside of a disjunction? That will be logically equivalent to negate each of the letters, distribute, quote unquote, distribute that negation in, and flip that thing that's attaching them, which I've been calling, just generically been calling an operation. Just two things that are attaching them. Oops. Okay. These two things together are called De Morgan's laws. Put a star, and I'll name it down here since I'm squished for space. De Morgan's laws for logical statements. Okay. A little bit of a detour there, but it was a good time to point that out since we had done the truth tables for both of these. And how do you prove that? So literally what we just walked through with doing the truth table for this and then doing the truth table for this and then saying, oh, look, the columns at the end are the same. We literally proved De Morgan's laws. Remember, to prove it with sets, we had to draw pictures and kind of shade in things. to do the proof for De Morgan's laws here, you just make the truth table for this side, make the truth table for this side, and compare them. So if you wanted an extra exercise, you could prove this De Morgan's law, because we didn't do this one, right? This is like the other version of it here. You could make a truth table for this side, and then a truth table for this side, and you should end up with the same thing on both sides. And once you've done that, you would have successfully proven both De Morgan's laws for logical statements. All right. Let's do let's see. I'm going to actually bring the book over now and see if they got a good example for us to do. How much time do we have? Oh, good. We're doing good on time. All right. We've got to do one with, that has 3 variables in it. I've been putting it off because it's a lot of work, but we should do at least one together. All right, so let's consider example 4. Let's make a truth table for P and Q implies not R. That's an R. So my letters I've named, instead of like A, B, C, I'm using P, Q, R. P's and Q's and R's are like kind of the traditional letters you use for describing logical statements. But also you can use whatever you want, really, it doesn't matter. But we'll use P, Q, R, and A, B, C a lot. Okay, when we set up our truth table now, we're going to have 3 initial base columns, not just the 2, not just P and Q, right? There's also another letter. Now, before you start writing, before you get ahead of me, just know that you're going to need a lot more vertical space for this one. That's why I'm worried about doing it here, because I need a lot of space, and I'm not convinced that I can fit it here, but I'm just going to try and see what happens. All right, so first of all, we're going to have initial columns, P, Q, and R. All right, so I need to think of every combination of truth values for these 3 before I even start thinking about the rest of my table. It would help if I had an idea for how many combinations there should be, right? Like when it's just P and Q, or just 2 letters, there's 4 combinations, right? True, 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 false, false, true, false, false. You throw another one in there, and now you've got, like, the first one will be true, 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 right? And then you've got true, true, false. And then, so you can see that there's going to be a lot, that there's going to be many more. How many more? Well, in chapter 7, we're going to look at counting techniques. Here, I'm just going to go ahead and tell you there's going to be 8. It's going to double. Each time you throw a new variable in there, it doubles. So if you only have 1 variable, there's only 2 possibilities, true or false. You have 2, then there's 4. That's like the classic one we've been dealing with. You throw another one in there, now there's 8. It doubles each time. And let's get on the same page with the way we list them. So let's start off with true, true, true. You're going to want your rows in the same order as mine, otherwise you're going to get super confused. So don't get ahead and start like just writing at any combination you can think of. I'm going to have a very particular order here, and I really recommend you follow it just to keep us on the same page. So first is true, true, true. Then true, true, false. Then true, false, true. Then true, false, false. Okay, I'm halfway. Oh no. Halfway. Notice the P here has just been true the entire time. So now basically what I need to do is do this exact same thing again, these 4 combinations copied down here, except P is going to be false for all of them. So what I'm going to have first is false, true, true. And then false, true, false. and then false, false, true, and then finally false, false, false. Just in case these last two rows are not, let's see, I'm trying to see, yeah, no, that is not good, so P and Q implies not part. All right, you're good, just wait 1 second, don't erase what you have, I'm just gonna try and readjust here. I'm gonna really try to maximize my space. Oh, let's do that. All right, let's put. Oops. Order. All right, there we go. Sorry about that. I wanted you guys to be able to see it. I could have just read the bottom rows to you, but that didn't feel right. I wanted you to be able to see it. Okay, what is the next column we're gonna need? Well, we've got a few pieces here. We've got a few pieces. We're gonna need the negation of R. Why don't we start with that? The negation of R. I see the negation. Any negations that are directly attached to a variable, I want to include. That is the negation of R there. So I'm literally just going to write this entire column flipped, right? So false, true, false, true, false, true, false, true. All right, there's that part done. And what's the other piece that I need here? Anybody? I need, yes, go ahead.
P and Q.
Yes, P and Q. P and Q. P and Q. Oh, and look at how I've planned this. There's my last column. Ha! All right, so P and Q is my next piece here. So I'm going to be considering these columns. Now there's a lot of them, right? And is there going to be repetition? Of course, right? I'm just considering these two and there's tons. Of course there's going to be repetition. That's okay. That's okay. So P and Q, a conjunction, a conjunction is only true when both inputs are true. So here I'm looking here. These two are true. That's good. These two are true. That's good. The rest are going to be false, right? The rest are going to be false because the only way a conjunction can be true is if both inputs are true. Looking at the combination of the rest of these inputs, at least one of them is false in every single row. So the rest of these are going to be false. So you should have 6 falses. You want to make sure things stay lined up, right? Okay, now my last column is the entire statement. How do I know that? Well, because I have the pieces that build the greater implication statement, the if-then statement, the conditional statement. I have the pieces, the first part, the P and Q, and the not R. These are the columns that I'm going to be considering in order to fill this column out. And I need to be thinking about it in the order from here to here, the order they appear here. So here to here, here to here, here to here. And I might want to think and remember that, sorry, spam calls. It's just distracting, vibrating in my pocket. All right, so I might want to recall that a conditional is only false with the combination true, false. So it's only going to be false with the combination true, false. So right off the bat, I have that in my first column. I have true, false, yielding a false. What I'm going to do is I'm just going to look for any other true falses, like true falses. And if I find any more of those will be false, right? And the rest are going to be true because I know how a conditional works. It's only false if I have the combination true then false. If true then false yields false. So let's look for those. Any more TFs? No. No. So the rest are true. You're going to want to make sure we're lined up here. I feel like I miscounted. Let's see, 1, 2, 3, 4, 5, 6, 7. That's good, 8. There we go. That's the truth table for this statement. P and Q implies not R. So why are these so useful? Well, imagine if I said a statement like, what if I assigned a little statement to each one of these letters? Because that's what they represent. They represent simple statements. So what if I said that this statement P is, it is raining, it is sunny, and it is windy. All right. So what if I just as an exercise, you don't have to write this down, but if P is, it is raining, Q is, it is sunny, and R is, it is windy. So they describe weather. And then I said, if I say the statement, if it's raining and it's sunny, then it will not be windy. And then I say, and then I ask you to look outside and say, am I lying? And you look outside and you see that it's raining, windy, and not sunny. Have I told the truth? Well, you're already lost, right? Like, how the heck could you keep up with that, right? You're like, okay, wait. You'd have to be like, what did you say? I got to write it down. This is much more clear, right? You can look at the combinations that you gave, the original combinations here, decide which combination you're falling in. Like, oh, it's raining and it's windy, but it's not sunny. That's this combination, so your statement was true. You know, that's just an example of the power of these truth tables, is they let you decode like these crazy compound statements that in English would just be just too much, right? Just way too much. Okay, so that's example 4. I'm going to go ahead and erase it. Let's talk about, yeah, we have enough time. I want to talk about a special kind of output again, not like a De Morgan's law. One minute. Just want to make sure I'm not missing anything before I. Oh, there's this positive. Yeah. All right. Here's the definition: a tautology. A tautology is a compound statement that yields truth value outputs of all true. I could have probably worded that better, but that's what a tautology is. All the outputs in your truth table at the end are true. So there's a real quick example of a tautology. Now in the homework, you might be asked, you know, is this thing a tautology? And all you have to do is construct its truth table and look at the last column and see if it is indeed a truth table. I'm going to give you, if it is indeed a tautology by looking at all of its truth values and seeing if they're all true. I'm going to give you a real quick example of one. Like, is C and not C a tautology? Nah, let me make it C or. Yeah, because that wouldn't be a tautology. C or not C. C or not C. Now consider this just in English. Let C be it is sunny outside. If I said it is sunny outside or it is not sunny outside. That's like a meaningless statement, right? Because it's always true, right? Of course, it's either always sunny or not, right? It's like those are the only two possibilities, right? But how does that look in a truth table? Well, if I've only got one letter, my truth table is going to be very nice and compact with just two possible combinations, true or false here. I don't have another letter. That's my base column. I also need to consider the negation of C. The negation of C, which is just going to be this column flipped. We haven't done one yet with just one letter. But when it's just one letter, you only have two rows. Your base column is just that letter up here, and then it's two possible combinations, either just true or false. And in my next column, I'm starting to build up this by getting the negation there. So I'm just taking the negation of C by flipping this column. And then I'm going to say C or not C, because I'm ready already to build the whole thing. And or is only false if both inputs are false. So in other words, both of these are going to be true. This is a tautology. Yes. A tautology is a compound statement that has only truth in its outputs. Cool. So that's just a small little definition. But I've found, when I build the homework, I'll put one of these questions in there because it's like a fun little definition, kind of, and it forces you to build a truth table. But the homework will, it generates problems based off of what I pick. And I've gone through the homework in the past, having just picked one of these, and it'll give you like 3. So just wanted to make sure I went over an explicit example here. They can get more complicated. It can be a huge compound statement and end up being a tautology at the end. It doesn't have to be this little tiny, compact, cute little example here. This is just a real quick one that I can plop down without needing the entire board. All right. So we're almost out of time. We still need to talk about 3.3 on Friday. I've already talked about part of it. Part of it is that logical equivalence with De Morgan's laws, but there's also some new definitions in there dealing with conditionals, namely converse, contrapositive, inverse, and biconditional. So in order to get ready to prepare for, because I'm probably going to go through it a little, 3.3. I'm going to go through it a little quick because I want a little bit of time at the end for you guys to ask questions for review, right? For review for the exam. So to prepare for 3.3, go ahead and read, let's see what page it is. Page 110, table 1. Just kind of look at those, just get acclimated to the words, those definitions of converse, inverse, contrapositive, and biconditional. Just kind of get comfortable with what that is. You don't have to go deep into the truth tables for those. We will do that together. But just kind of, it would be really great for me, like time-wise, if when we started the lecture for 3.3, I could just plop that table down, you guys be at least familiar with the words and the symbols, and then we can go straight into examples of each. Now I need to give you some problems to mark for review for 3.2, which is what we finished today. Let me see what I have here. Let's say number 7, that's a tautology problem. 13 would be good. That's a word, like going from words. So that's kind of putting together 3.1 and 3.2. Oh, that's all they give here. Surely, sorry, there's got to be something better here. Or not. Try number 3 as well. Try number 3. All right, 3, 7, and 13 from 3.2. All right, you guys are good to go. I'll see you Friday.
Are we gonna talk about